where the other h bar goes. Del down A on the psi, acting on the psi bar. So now I have 1 minus too much, so I get rid of that. But then there is an I too much. I need to modify this, so I get a minus I. That's this. Minus, now I do the psi here, and then comes the del A minus I h bar. Aha, hang on, I put this out again. Okay, so I guess this yields a plus here. Is that right? I got myself confused, I'm sorry. So this is right. Okay, so now I go to this one. I have a minus h bar by 2m in front. I write here minus del A minus I h bar del A psi bar. Okay, but if I did that, I got rid of the h bar, that's right. I pulled the minus in, I think that was that move, and then I have the I there that compensates for that. I think that must be it. In any case, what the claim is, this is just to see more easily what the claim is. If you define rho to be psi bar times psi, and you define a vector field, covector field, because messed up with the that's because we don't write the metric explicitly. So you write this as del A psi times psi bar minus psi del A psi. Something like that. So now the I in front cancels. Okay, this is a little messed up. So maybe there's an overall I somewhere. If you write this curve, then you can bring this to the form. So have some factor in front here, alpha. You can bring this to the form that the d by dt rho plus the gradient of this vector field of this current equals 0. Right. So this guy here is that guy over here. And the only thing one has to get straight is the i's there. I think there is an... If you kill this I against that I, so this line no longer is valid, this I against that I, you have a minus sign there, then you get a relative minus sign in here, if you... So you can pull it in here and there, something of the sort, then it would be rather the other way around here, and an overall I here. Something like that, if you figure it out, okay, this is now... So you get this continuity equation. Well, it's rather artificial. We identified this guy here, which you get from here, because it's kind of like by the product rule, this works like. But this thing on the right-hand side looks extremely artificial, right? I mean, why do you write this down? Well, the point is, it doesn't matter what this expression is. What to learn about is about the change in time of the rho, which you want to interpret as your energy density, as your probability density. So it actually doesn't matter what exactly here is, as long as it can be written in the form down there. And that's already clear in this line, that you can this guy out, and then there is something here. So therefore, this means that if you take the integral over all of space and you exchange it with the derivative, rho over all of space, what is that? That's the integral over all of space of the del A of something, of JA. But if you go over all of space, if this is over R3, then there's no surface term, and this here is a pure surface term. So the result is 0, right? Aha! So that means the integrated, so the total probability does not change in time. Perfect. And this is not a trivial result, because our definition here only depends the psi as it depends on the spatial position x. This has nothing to do with time. You know that you have a spatial probability density, the Schrödinger equation evolves it further, 10 seconds later it looks like this and that. So the question of whether this is positive, well, that is true against time is by definition because the absolute value is correct. But the question of whether the total probability is conserved, that's a question that has dynamical content. You need to look at the evolution equation for that. So in fact, so the upshot is that the axiom 5 are consistent. The probability with the, well, they are consistent because 5 tells you how to interpret the whole thing. Okay? So everything is well. You can interpret the Schrödinger equation according to this probabilistic interpretation. You see this quadratic thing, so this makes all the funny effects. Right? The Schrödinger equation itself, forget about the blue psi bar, is a linear PDE. This is particularly simple. Lots of the quantum mechanics special stuff comes in by interpreting the result this way. Okay, good. So that's it. Now, in fact, so second, heuristic derivation of a relativistic quantum mechanics. In fact, when Schrödinger thought about this stuff, he did not write down the Schrödinger equation, because he thought, why would I bother with the non-relativistic energy-momentum relation, because he already knew it was the energy-momentum relation of special relativity he implement. So in fact, the equation we're not now going to derive is the so-called Klein-Gordon derive, right? Motivate is the Klein-Gordon equation and it should be better called the Schrödinger equation, because Schrödinger found it first. But then he discovered a serious problem with it, and that's why he abandoned it. He went to a non-relativistic case where the problem was not present. Okay? So heuristic deviation is this. So you recall that in what is Newtonian physics? What is non-relativistic physics? Mechanics. Well, so what we already used, relativistic mechanics is you consider space-time, but Newtonian space-time, which is a smooth manifold, and then there's a special thing. There's something called an absolute time, and mathematically speaking, this absolute time is a smooth function on the manifold that has nowhere vanishing gradient dt. That's an absolute time. So absolute time that is ticking in blah, blah, blah. He means that. He means to say that. He doesn't have the mathematics to say it unambiguously. That's what he means. And then Newtonian space-time is not equipped with a metric. Newtonian space-time is equipped with a so-called connection. You can't with a metric, makes no sense, but there's a connection. And the connection says a particle moving under the influence of no forces, or says a particle to which forces can't move, moves along a straight line. This first axiom defines what a straight line is. Actually, this here is the so-called parallel transport, and that defines geometrically what a straight line is. So this is a torsion-free connection. And then Newton talks about that time flows uniformly, and that hardly means at the speed of 1 second per second. What he means by that is that, well, he means it, but I think Newton means a lot of this, and you can read this, but again, he didn't have the mathematics to say it clearly. Time flows uniformly means, okay, that's Newtonian space-time, and if you use this here, you can find a stratified atlas, such that the picture of Newtonian space-time is like this. You have all your equal time surfaces. There is such a thing as equal time surfaces, because you have this absolute time, and you have like a lot of R3 photographs for each point in time. That's the picture of Newtonian space-time, and that's just what it is, okay? And also, so space-time is very often associated to relativistic physics, but that makes zero sense, because it's not just the right data structure to talk about what happens where and when, the so-called events. Now, relativistic space-time is distinctly different, and well, in principle, you would have to be a madman to change this picture, because it makes so much sense, right? When happens what? Because Einstein, contrary to how it's sometimes presented, didn't think about space and time because he was so genius. He thought about space and time because he had to. Because even within this picture, Maxwell formulated his Maxwell equations, which came out of observations of Faraday and the Ampere law. And if the Maxwell equations are right, that forces us to a different picture. Maxwell theory, if right, forces one to a dramatically different picture, or different theory of space-time. And that's, of course, the relativistic space-time of Einstein. What is relativistic space-time? Well, you also know from the previous mechanics course from the last few lectures, relativistic space-time is also a smooth fold of dimension 4. But instead of the time, having absolute time and the connection, there is one single structure replacing the two, and that is the so-called Lorentzian metric. Lorentzian metric, and Lorentzian refers to its signature. So it has a signature plus, minus, minus, minus. For example, it could also be minus, plus, plus, plus. Anyway, one sign like this, the others differently. And there's one more ingredient, however, it's the G that replaces both structures. And from this G, you can actually derive a connection on space-time. That's a very special one. It's one that's totally compatible with this G. And now the picture is dramatically different, because at every point of space-time, you have in the tangent space, you don't over-interpret this picture. This is a little cone in each tangent space, and the tangent space attached here. You have at every point in space-time, well, first of all, you have a double cone because you have a metric. Right. So it can look rather wild. The Einstein field equation that governs how these look, depending on the content, can have a boring situation where there is a coordinate system that they all appear like this. But really, this is always at this point in this tangent space, at this point in this tangent space, and so on. And there is an extra structure here that we call capital T, which has absolutely or very little or nothing to do with this T. This capital T is a nowhere vanishing time-like vector field that just can be used to select one of the halves. And then you have something like this. And that is the space-time structure. Right. There's not one big cone like here or several big. At every point there's a little cone. That's the space-time structure. Okay. Yes.
So would you say that the T is then also derived from the G, or do you not?
No, the T is extra. The T is extra. The T is the big. The middle T. No, there is no little T. The middle T is in this structure. If you took this to an extreme, you could put the 0 here, and the cones would open more and more and more, and it would look like this somehow. But this limit makes no more sense, because in the limit this would no longer be a non-degenerate metric if there's a 0 up here, and then the whole construction breaks down. So it's very difficult from this, or subtle, from this picture to get this as the limit case. There are very quick arguments that look very good until you start pushing them. Okay? No, so it's really the absolute time and the connection meld into one structure, which is the Lorentzian space-time metric. That is just the way it is. Okay? And this T here is the dirty secret of relativity theory, because in relativity we talk about time, and here you can say what is forward in time and backward in time. Well, a vector, so that if you have a world line that runs in space-time, so the history of some particle, histories look like little curves in space-time, right? That's the beauty of this data structure, that everything that ever happened to the particle is in there, so you play out, you look at this, and you know what's happening. Now, the question is, you can have a curve running like this, so you can have a curve running in the opposite direction. Now also here you have a definition, the curve, in order to be the history of a particle, must run forward. But what do you mean by forward? Well, it means that the tangent vector of the curve is everywhere, if you apply the dt, the gradient of the absolute time to it, must be greater than 0. This is the time orientation is also in this absolute time function. Whereas here in a Lorentzian manifold, there is no such thing. You cannot distinguish, if you only look at the metric, this part is going from this part. You have the paths, but one is preferred over the other. Extra nowhere vanishing time-like vector field. If it's nowhere vanishing, then it's...
肥満体質のあなたに超朗報。どんな人でも強制的に痩せてしまう減量ドーピングが今話題になっているんです。たった1ヶ月でマイナス6キロは当たり前。海外ではマイナス20キロ痩せた人まで続出しているこの減量法。痩せたいけど食事制限や運動は絶対にしたくないっていう人こそ試してください。なぜならこれは強制的に痩せてしまう減量法。どんなに意志が弱い人でもお構いなしにどんどん体重が減っていくんです。そんなダイエット危なそうって思うでしょうか。ご安心ください。これはケトジェニックダイエットという医学誌にも掲載された食事療法で、健康面や美容面としてもメリットが多く、管理栄養士も推奨するほど安全な減量法なんです。基本的に私たち人間は糖質をエネルギーとして活動していますが、糖質を取りすぎると脂肪になってしまうのはご存知ですよね。そこで糖質ではなく脂肪をエネルギーとするケトン体体質に切り替えるというのがケトジェニックダイエット。糖質を必要としない体になるので、脂肪が溜まることはなくなりますし、すでに体についた脂肪はエネルギーとして積極的に分解燃焼されるので、最短で痩せていく効率的な最新ダイエットなんです。ただしケトン体体質になるには厳しいルールに従ってタンパク質、食物繊維、ミネラル、脂肪酸の量を調整する必要があります。食事は主に脂肪と限られた量のタンパク質、ほとんどの炭水化物や人工甘味料を含んだダイエット飲料でさえ飲めないのです。そんな生活を続けるなんて絶対に無理ですが、実はとっても簡単な裏技があるんです。それはズバリ専用のサプリメントを飲むこと。本来計算して食事を調整しなければなりませんが、あらかじめ計算されたサプリなら短期間で強制的にケトン体体質に変えることが可能。私がおすすめするのはケトジェンヌというケトジェニックダイエットランキング5冠を達成する超人気サプリメント。質の良い中鎖脂肪酸やアマニ油がケトン体回路のスイッチを強制的にオン、サジエ X、スピルリナ、アシタバといった3つのスーパーフードで豊富なミネラルとタンパク質を吸収します。さらに水溶性食物繊維の難消化性デキストリンが余分な糖質の吸収を抑えて排出。大豆イソフラボンとオリーブ葉が食物繊維を後押ししながら美容面をサポート。この設計がケトン体体質に速攻で変えるほど優れているそうで、サプリメントでありながら医学誌にまで掲載。有名企業で数多くの講演を行う管理栄養士もケトジェンヌを推奨するほど。そしてケトジェニックダイエットはとにかく短期間で痩せるのも大きな特徴。たった7日間で見た目が変わる人も多く、その効果に 92.5% が大満足と回答しています。医学誌に掲載されるレベルなので当然かもしれませんが、ケトジェンヌは通常価格6980円の高級サプリメント。それでもテレビで芸能人が紹介した時には即完売、一時は販売停止状態が続いていました。今回はその上げとして特別キャンペーンをご用意。通常価格6980円のケトジェンヌ1ヶ月分をなんとたったの300円、送料無料でご提供いたします。さらにここまで動画をご覧いただいた感謝を込めてもう1袋無料でプレゼントさせていただきます。今回のキャンペーン定期コースではあるんですが、30日間の定期解約保証付きなので、1ヶ月飲んでみて効果がなかったらなんて心配は必要ありません。ご自身の体でケトジェニックダイエットの力を実感してください。もう一度言います。医学誌にまで掲載されるほどのダイエットサプリケトジェンヌがこの動画限定で300円でお試しいただけます。もちろん送料は無料。全国どちらにお住まいでも送料を気にせずお申し込みください。さらに今お申し込みいただいた方にはもう1袋を無料でプレゼント。この値段でケトン体体質になれるのはありえないレベルなので、今回が最後のご案内になるかもしれません。特別キャンペーンのお申し込みはお客様情報を入力するだけ1分ほどで完了します。申し込み後は1週間程度で届きますが、キャンペーン実施中ということもあり、応募が殺到して届けまでの時間が長くなる場合があります。そうなる前に今この動画をご覧のあなたは今すぐお申し込みを完了させて、誰よりも早く楽して痩せるケトン体体質を実現してください。お支払い方法はクレジットカードの他にコンビニ後払いもご用意しています。クレジットカードを持っていない、入力するのが面倒、届くまで心配という方は安心して後払いでお申し込みください。こちらの特別キャンペーンは在庫がなくなり次第終了となります。今すぐ動画下の商品ページボタンをクリックしてお申し込みください。
Hi everyone, today I'm going to talk about using pre-computation to build interactive deformable scene simulators. Before I do that, I just want to find the mouse that makes my slides work. I guess it's this one. Yes. So I want to have a dedication to my son who was born 2 months before the SIGGRAPH deadline, and this was really lucky because he really helped us finish the paper, I think. And he's a good critic too. I mean, he's pretty skeptical, and I think he had some good questions for us. Like, if you look into his eyes, you can kind of see him saying, gee, aren't chips fast enough? Can't you just simulate it all? Why pre-compute anything? And so this leads to my motivation. Basically, exactly, he's exactly right, you know? And so the real issue here is dealing with complexity. There's so much complexity in the world that people in this room all have in common the fact that we probably all want to see more things simulated. Deformable systems are well understood, but they always take a certain amount of time to compute, and it can be expensive for large systems. Even this simple plant model involves fairly complex collisions between the leaves, and then when you're done with that, you still have to render it. So we also like to think about how we can pre-compute illumination for these kind of deformable models so that this can be all pre-computed. The other motivation for this is that interactive applications, ideally you'd want to simulate as many of these systems as you can and basically do it at little cost, so you can focus your resources on more difficult problems that can't be pre-computed. The other motivation is that we'd like a simulation that is very simple. Building real-time simulators that are robust and can deal with very complicated systems is difficult, and we'd like to basically cheat and avoid this entirely. So the overarching motivation is that no matter how fast CPUs or GPUs become, we can still do more than 5 million times as much work on one day on a computer as we can do in 160 Hz frame of simulation. So we think it behooves us as a community to figure out how to take advantage of pre-computation for deformation animation. Certainly, global illumination people are interested in this. Okay, so here's a preview of some results. A plant moving with interesting soft shadows. So you probably don't have a hula dancer on the dashboard of your car, but I always kind of wanted one, and so we decided to make a hula dinosaur, and this is what it looked like on our road trip to San Diego. Another example is having a piece of cloth hanging on the door, so you can move the door around and have the cloth move realistically at basically no cost at runtime. So the overview of our work is basically we're going to model physical systems by tabulating their dynamics by observation. The key thing here is that we're not trying to solve all simulation problems. We're just trying to simulate a particular system under very particular interaction conditions. So for example, the cloth on the door, we're going to see how this cloth moves when we shake the door around, for example, in Maya, and then get some corpus of motion, a long time series of behaviors of this piece of cloth. Then we can analyze this cloth to discover the impulse response functions of that system and use these impulse responses to replay the dynamics for very low cost at runtime. We can also take advantage of the fact that we pre-computed a representation for the state space of the model by also pre-computing radiance transfer representations for the space of known shapes. Finally, we can put these all together to replay these motions and appearances at runtime by simply doing table lookup operations. And this is not part of the presentation. Why did that happen? Okay, so there's a large amount of related work here on deformation. Certainly there's a large body of work in engineering and certainly in graphics. We build on this by using this as pre-computation tools for building these models. The work on pre-computed deformable models has mostly been limited to linear deformation, linear elastostats using Green's functions, or elastodynamics using modal analysis. There is some work on using subspace projection methods for building fast numerical integrators using PCA, Cartan-Loaf transformations. Our goal is to basically avoid runtime time stepping entirely by replaying impulse response functions. Also, shape approximation is related to other work in computer graphics. Work on pre-computing data-driven nonlinear models has also occurred in graphics. There's supposed to be a video there, but basically our goal was to replay motions in our database. So for example, if we have a cloth model or the plant model that has significant complex self-collisions, by replaying motions we guarantee that what we see on the screen is robust, and we also avoid the problem of having to interpolate or generalize motions from a possibly incomplete database. We do this at the loss of fine-grained control, but we gain this robustness. Replaying motion segments is also related to other work such as video textures and motion graphs. Of course, in our case, there's a different physical context. And also, we build on work for pre-computed radiance transfer in the sense that most of the work in this area has occurred for rigid models, and we look at deformable models for diffuse interreflections. Okay. So the approach we use is to tabulate state space model dynamics. So what is state space? So state space basically consists of a bunch of states represented by X consisting of the shape or position of the deformable object as well as the rate of change of that shape, the velocity. To give you a very simple example, we'll just consider a 1D damp spring mass system, and here the Q represents the extension of the spring. So the dynamics of the system then behave in a two-dimensional state space consisting of position and velocity. So if we apply an impulse to the system and discontinuously change the velocity of the system, so it moves from the origin up to some non-zero velocity, and then we can integrate the dynamics and see how the system responds. So that's basically an impulse response function for this simple spring mass system. The key thing from a data-driven point of view is if we tabulate that, then we can simply replay that motion at runtime to resolve an impulse applied when the system is at rest. Of course, we may want to apply impulses when the system is not at rest. In that case, you can imagine that we're integrating the dynamics, but then we apply another impulse while it's still moving, and then some other dynamics ensue. Well, we can tabulate that too. So then we have two impulse response functions tabulated at two locations in our state space. You can imagine that by repeatedly doing this, then we can build up a representation for the impulse responses of this system in this two-dimensional space. So the problem with this sort of generalization, this analogy, is that there's enormous problems with dimensionality. If we take a spring mass system representation of our Maya cloth, and each particle in the system has about 6 degrees of freedom in state space, so that an n-particle system is in 6 n dimensions, so that our cloth model is approximately 20,000 dimensions. So if we try to tabulate that space, there's an incredible amount of space there, and it's going to be a waste of time, if not impractical. The point is that it's kind of a moot point because we don't even need to do this. So we use a data-driven approach by looking at how a particular system behaves under very particular interaction conditions, such as how this door moves when I move it at a fixed velocity, either clockwise or counterclockwise, or have it at rest. So I don't want to take this piece of cloth out the door and shine my shoes with it and throw it in the wash. I just want to see how it moves when I move the door. And so it's a very particular, simple thing. So the key thing here is that by restricting the interaction, we can tabulate this using impulse responses. And then we can exploit the fact that the motion has a very particular structure, and we can do two-dimensional model reduction, or basically least squares projection. So I'll first talk about this and then go on to the more interesting part of impulse response functions. So basically, if we're going to tabulate all this data, we need an efficient representation. We're basically going to time step a system and see the kind of behaviors that emerge, and then take these different shapes that occur, group them together, and then try to figure out a simplified representation. It turns out that this can be immensely simplified for many systems, but not all. If we first extract the displacement fields from these models and put them into the columns of a large matrix, then the range of this matrix describes all possible shapes. So in practice, this can be an enormous matrix, like several gigabytes or something, but it tends to have a very simple structure. In particular, if we take this large matrix, we can do SVD on it to factorize the system to discover the low-rank structure of the system. So here I've shown that in fact the matrix is quite simple. It can be approximated by a very low-rank matrix. This picture is actually enormously exaggerated because for a dinosaur we had approximately 20,000 time steps here, but the actual amount of information was embedded only in 12 dimensions for this model, using the time step using some implicit Newmark integrator. So basically, what we want to do is discover this reduced deformation basis or nonlinear modes, and then find the reduced coordinates that describe the behavior of the system in this reduced space. I'll first show some examples of these deformation modes. Here's the dinosaur example, and so here's the first mode, sort of a side-to-side motion, and then moving up and down, and some other different nonlinear modes. And so the key thing about these modes is that they essentially are physically based splines that help us solve the animation problem for this physical model. Okay. So here are singular values for the deformable shape. You can basically see that there's fast convergence for this model, and that in practice we only need a dozen modes to resolve the behavior to approximately 0.5% accuracy. The rest of the dimensions are not relevant. Again, looking back at the factorization, the other key part is the coordinates that describe how each pose has a particular coordinate in this reduced dimension. So if we take this cloth model, these 10,000 time steps for this model, and we do this projection, then if we look at the system projected in only the first two spatial dimensions, we get some interpretation of what a piece of cloth looks like. And this shows sort of three lobes associated with hanging down or pushed against or away from the door, basically the motion of the center of mass. The other 60 dimension in the state space model aren't shown. Okay, once we can represent data, then we can actually start tabulating something. So the key thing to tabulate is the impulse response function. This is our data-driven modeling primitive. We tabulate these throughout the state space, and they describe the response to the system, including all interesting self-collisions and so on. So for a really simple example, the dinosaur, if we apply some impulses, these are body impulses associated with rigid body motion, the system responds. Basically, we want to tabulate these systems for all different shapes of the model. Okay, what is an impulse response function? Still go into a little bit more detail. If we have a state in the state space X and we want to find out the response of the system in that configuration, then what we do is we apply an initial impulse with delta I, which is a potentially strong impulse, and then we time step the system after that for t time steps using the persistent forcing parameterized by the alpha F parameter, which describes things such as the air damping on the cloth when the door is moving at a particular rate after it's discontinuously moved. And so after time stepping it then for t time steps, this gives us an impulse response that can be played back for those time steps. The key thing here is to limit the type of interaction by being very particular about what we're simulating. And we use impulse palettes as combinations of alpha I and alpha F parameters to describe particular types of interactions. This is motivated by the fact that often in virtual environments or video games, interaction modalities are limited. We can't maybe tie the leaves of the plant in knots, but we can maybe shake the pot around. For the potted plant example, it's very simple. The plot has two rigid body impulses that can be applied to the leaves associated with discontinuous accelerations. These are left and right motions. So the key issue here is then how do we use this to actually pre-compute the impulse response database? A simple example here is basically if we take n time steps that we want to use to generate this database, we first go ahead by randomly picking a particular impulse response, here shown in blue, and then integrating it for some random amount of time chosen from some distribution of time intervals, such that we get enough long time intervals that we can play the motion essentially to rest. We then take these motion segments and put them in a database, and again continue to randomly apply appropriate possible impulses to the system to tabulate different dynamics. We then proceed this way to pre-compute several hundred different impulse responses of the system. And then what we do is we throw away very short impulses. These aren't wasted, they simply help us span the phase space of a model. And then what we do is we simply keep the long ones. It's also possible to extend ones that you want to have longer just by computing more motion for those particular dynamics. Once we have all this stuff, then that's basically our impulse response function database. And we can use that to replay dynamics. So for the potted plant, it had two impulse responses. If we project the reduced coordinates into 2 dimensions, you get some weird looking thing like this, and that shows basically all the different responses of the system, and there's all kinds of collisions embedded in higher dimensions as well. So if you see how the actual index responses are indexed when the pot has motion changes, it makes a little more sense about what actually is going on. And we'll show a demo of this later. The dinosaurs are very similar. Again, in this case, there's just 5 rigid body impulses applied, and we tabulate these throughout the phase portrait to build up another representation of the dynamics of the system. Here is another impulse response database projected into 2 dimensions. The colors here correspond to the particular impulses. And again, it makes more sense when you can see them indexed by the particular motion in the simulation. Here the dinosaurs shown in our trip over the Rocky Mountains. Okay, so the cloth on the door is similar, but it involves air damping as well. And but essentially the key part is that it has sort of 3 lobes associated with the blue, which is the cloth hanging down when the door's at rest, and then red is when the cloth is pushed against the door, and green when it's being pulled away from the door. So here you can see the door moving and pulling out impulse responses out of the database in order to play the motion back. Okay, so once we have this large database of shapes and motion, we can then go ahead and pre-compute an illumination model for it. This is the second contribution of the paper. Basically, we use radiance transfer, which is a wonderful thing and works very well for diffuse interreflections. The key thing with this approach is that you can exploit the fact that the excitant radiance of a vertex is linearly dependent on the incident light field. In our case, that's no longer true because the excitant radiance is now a nonlinear function of both the incident light field as well as the shape parameters from a deformable model. So what we do then is, given a database of different states, what we do is we can just pre-compute radiance transfer models for every single state. This will work fine, except that we have an enormous number of states, maybe tens of thousands. So pre-computing that many radiance transfer models is going to be expensive and a waste of time. So what we do is we instead cluster the states in different shapes into particular groups which are similar, and then pre-compute radiance transfer models for each one of these clusters. So given a radiance transfer model, we basically can extract a large vector that describes all the information of that transfer field. We then pack those radiance transfer fields into a large matrix and then do data reduction to expose the low-rank structure of the system, and then use these reduced radiance transfer vectors and the coordinates of the radiance transfer models at each of the clusters to describe how the system appears. And then we can interpolate these coordinates over the entire database to figure out how every single state will have a radiance transfer model. So if we look at the cloth model, basically that's what the radiance transfer model for the cloth looks like, projected in the first two dominant components. It doesn't really make a hell of a lot of sense to me either. But basically, if you look at the particular modes, again, here's some more stuff that shows basically the types of radiance transfer modes that are solving the appearance problem for this deformable model. The first mode, the second mode, again, you can see shadowing effects, the different types of lighting effects that are important, some color bleeding effects from the red on the ground coming up onto the side of the dinosaur, and so on. And some bottom shadows. So you put it all together, then you get dynamic color bleeding. Here you can see the red from the ground bleeding onto the side of the dinosaur. You can also get soft shadows. Again, we're using 4 bands of circle harmonics, so it's pretty blurry lighting, but the blurriness actually works in our favor because it lends itself to a statistical approximation under the effects of deformation. Here we're getting soft shadows between the leaves. When the leaves come down, you can see the shadow appearing there. And when you animate that, then it has a fairly compelling look to it. Okay, so at runtime, what do we do then? We basically replay impulse response functions with their corresponding radiance transfer models. So what we need to do then is at each time step, look up these reduced displacement and radiance transfer coordinates, which are stored at the current state that we're animating. And then we just need to do a dense matrix vector multiply to figure out the corresponding displacement and transfer vectors for that state. And this can be done easily in software or also in hardware. In fact, we do most of our work in software because it's quite fast. So for impulse resolution is the other major component. We're playing some impulse response function back, but then all of a sudden, bang, there's an impulse to shake the pot the other way, and the system gets excited. So we have to find the nearest impulse response function. So we're tracking this impulse response function along, and all of a sudden an impulse occurs. So what we do is ahead of time, we cache references to the nearest impulse response functions for the different colors in our impulse response palette. And then we use that impulse response function to resolve the impulse. And basically what we do is we find the offset between the current state and this impulse response function state, and exponentially decay that offset along the new impulse response to basically resample it and resolve the impulse. This allows us to resolve impulses at runtime for basically no cost and to replay the dynamics appropriately with some slight approximation. The other thing about this is we can also do the same thing to compute the reduced coordinates for the radiance transfer model. Okay, so the results of the time. This is, in fact, undersampled. 200 poses was not enough to actually resolve all the fine shadows in the model. That leads to some variations in lighting. For real time, we can simulate the deformable object at about 350 frames per second. That's basically render bound at that point. We're only getting 100 megaflops from our software. When we use radiance transfer, we get about 149 frames per second. But we're actually fixing the light vector in this case so that we can get better performance. Otherwise, it's about 30 frames per second in software. For the dinosaur, we had about 33 hours pre-computed at a low resolution using the implicit Newmark integrator. And the light is only 50 poses, but because of the resolution, it took 74 hours. For real time, we can simulate the dinosaur at about 170 frames per second, and with light, it's still certainly faster than real time. In hardware, it's even faster. In this case, it actually fits into a Vertex program. So we're then going to show a live demo now. Kayvon is going to show the plant model. So if we can switch to that screen. So on the left, you can see the state space viewer that shows all the different impulse response functions, and those little dots are represented by some radiance transfer data. You can see that when he shakes the pot around, different impulse responses are played back. So if we just zoom in on the plant. So what was I going to say? So basically, the plant was pre-computed using Abacus, using an implicit Newmark integrator with thin shell elements and some frictionless contact. It was not particularly efficient code. In fact, it took about a week to pre-compute the motion in this database. So I guess the meta point is that, aside from don't use that code, is that even using incredibly inefficient code, you can still generate real-time simulations. The radiance transfer only took about 12 hours, I think, to pre-compute for this model because of the low polygon count. It simulates at about 470 frames per second for deformation only, and in software, it's entirely render bound. So you can basically simulate dozens or hundreds of these models. And for the radiance transfer, it drops down to, I don't know, my slides are gone, so I'll tell you in a second. So thanks a lot, Kayvon. Okay, my statistics are here. Basically, with the light vector fixed, it's about 200 frames per second in software. Okay, in summary, we've shown how to pre-compute databases for interactive deformable object simulation. By constraining the type of interaction that can occur, we can simplify the task of actually pre-computing interactive motions using impulse response functions. We've also shown how to build radiance transfer models which support deformation for diffusion and reflections. The sort of end result is that this is a very cheap way to simulate deformable objects for cases in which we can pre-compute them. Conclusions of future work, we sort of overestimated how difficult it would be to simulate these deformable models by pre-computing them, and we should have actually considered more complex models and a broader range of interactions in retrospect. One issue that occurs is that when you have the cloth model that has all these self-contacts, that when you introduce errors associated with model reduction, that can lead to visual artifacts associated with self-intersection. And so in practice, we need a slightly higher approximation error for those models, lower error tolerance. And so other things that can be done are to certainly build better data representations. I know that the dinosaur model squishes by a good factor of 100 using wavelets on that mesh, and there was also a paper in the radiance transfer sessions that suggests that radiance transfer can be compressed. Certainly, if you want to compress it, I'm sure there are ways to do this. We need better pre-computation algorithms to more intelligently sample the states of these models, and we also need better ways to figure out what states should be rendered for radiance transfer and how to interpolate them best most efficiently. Also, in general, we're really interested in finding out the limits of precomputation for simulating very complex systems. So I'd like to acknowledge the help of several SIGGRAPH reviewers for helpful comments, NVIDIA, Chris Twigg, Matt Trenikost, and I'd also like to thank my son for his continued interest in deformable objects, and I'd like to thank you, the audience. Thanks a lot.
So we have time for just one question.
Sure, Caltech. So one alternative would have been to actually do the time stepping in real time while you're running. Then you would have less to pre-compute. Now you're trading off against having to do some computation at runtime, but it may be entirely feasible, and then you can sample the space better, guessably. Consider that.
Yeah, so that's a really good point. In fact, that would be an excellent thing to do. Certainly, that would be an excellent and intelligent thing to do for pre-computation if you wanted to do that. So the one thing we're trying to trade off was how you can actually pre-compute a space of deformable shapes for the illumination, and so we decided to go with the sort of the brute force tabulation. In one hand, it does limit, this aspect that you're talking about, but it also allows us to find sort of the best global basis for the model to find a simplified representation. So although we pre-compute a lot, the actual model is very small. In fact, the plant model is only 800K, just floats. So it's a very good point, though.
Let's thank our speaker. So in this paper, we're presenting a new method for computing single scattering or direct illumination inside of refractive objects. And this is a very difficult problem, but it also creates very visual-rich effects. So here we see on the left an animation of a light source spinning around a scorpion inside a piece of amber, and you can see the beams moving around in complex patterns on the scorpion. And here on the right, we have a light source spinning around above the sphere and creating all these complex volume caustics inside the sphere. And so even though the geometry may be fairly simple, the refraction can actually create very complex effects. So let's set up this problem. So suppose we want to compute a pixel. We start by tracing an eye ray until we reach some point v where we want to compute the illumination. So this could be a surface point or a volume scatter point, and then we want to compute the illumination from a light source L. If there's no refraction, this is a trivial problem. You just connect them with the shadow ray and compute the illumination. However, once you have refraction, you have the problem that the light bends when it enters the media. So finding this path becomes quite difficult. Moreover, you may actually have many such paths. So in this case, there's two distinct paths connecting V to the light source L. So is this important to actually handle correctly? So here's an example with a glass tile, and on the left we've computed it where the shadow rays ignore the refraction, and on the right we've computed it with our method. And you can see there's these characteristic caustics that give the glass tile its appearance. And if we simply ignore the refraction, we get the wrong appearance. It looks like a completely different material. So besides the bending of the paths and the multiple paths, we also want to deal with shading normals and potentially boundaries that have very large meshes. So shading normals are extremely common in computer graphics, used to add detail to geometric meshes. Examples include interpolated normals, bump maps, normal maps. And when combined with refraction, these significantly alter the pattern of the light inside the object. And so it's important to actually deal with these explicitly. I'll just bring up a couple of limitations. We're only going to be solving for paths that cross the boundary exactly once. So like the path on the left, the center path with its extra internal bounce, or the right-hand path which crosses the boundary twice, we're not going to find. We're only going to find paths like the one on the left. And moreover, because we explicitly find all the paths, when there are a very large number of paths, and there can be, the costs will increase. There's been a lot of prior work in this area. There's been a lot of work on diffusion in multiple scatter, but we're only going to talk about single scatter in this paper. You can solve this with Monte Carlo, but finding the directions that lead back to the light source get extremely difficult when the light sources are small. It's been approximated with beam tracing, particularly for underwater illumination. You can solve it with photon mapping, but because all the illumination inside the refractive object is caustic, you can't use final gathering. You end up having to blur by your photon map reconstruction kernel. And lastly, it's been solved using Fermat's principle, particularly by work by Mitchell and Hanrahan from 1992, where they used Fermat's principle and Newton's method to solve for paths. They showed results for reflection, but they also discussed how it could be done for refraction. But there were several limitations to their approach that limited the usability. It only supported geometry that was defined as implicit surfaces. It had no way to handle shading normals, and it required a somewhat expensive 3D search. So our contributions in this work is we're going to support triangle meshes with shading normals, which is the single most widely used geometry format in graphics. And this required a fundamental reformulation of the problem, some new search methods, intensity equations. We provide hierarchical culling to deal with more complex meshes, and we demonstrate both CPU and GPU implementations. So here's an outline of the talk from here on out. I'm first going to discuss the half-vector formulation, then how we solve for the paths through a single triangle, the hierarchical culling for meshes, and then present some results. So the previous work, this has been done using Fermat's principle. So you define the optical path length, which is just the distance along the path, weighted